Welcome everybody. Let's get started. So it's my pleasure today to introduce Carlos Benavides, who's coming from Italy, right? So he's a Marie Curie fellow at the University of Trento, Italy, very nice place in mountains. So his research is focused on many body phenomena in general. In particular, he is expanding a lot of interesting techniques that people developed and he and collaborators also developing a fermionic problem to problems which involve bosons or spins, essentially other many interesting systems. And Carlos did his PhD in the University of Zaragoza, Spain, 2016. Then he got the next step fellowship at Max Planck Institute for Complex Systems in Dresden, Germany. And after that, he got the Marie Curie fellowship. So today he's gonna tell us about quantum many-body systems, exact universal ansatz for quantum devices. So please help me to welcome Carlos.
Thank you for this introduction. This is my second time in Toronto, and I think it's not the last one. I am very happy to be here, and actually it's a very stimulating intellectual place where it's not the, it's actually completely true. I have had very good ideas for my research in the visits here, the group of Arthur or other groups in the university. So I am starting feeling at home here in the university. So this research started from the point of view of fermions, because fermions are everywhere, and in particular they are important in quantum chemistry. Molecules, reactions, metals, solids. Essentially, this is why fermions or electrons have such a paramount importance in the problem of quantum many-body physics. And this is why there are so many methods, essentially from the started in quantum chemistry, but also in condensed matter, where people wanted to understand the complexities of the interaction between fermionic particles. Now, what is somehow is quite interesting is that in many situations, the one particle description is quite good. This is still, to me, is a very surprising thing, because the band structure of solids, in many cases, gives you a lot of information, actually enough information to predict the behavior of the solid. And also, Hartree-Fock theory could be, okay, you say it's not that good, but Kohn-Sham DFT is actually quite good in some situations. So still in that one particle description of the problems, it is quite good. But there are regimes where you really have to consider correlations, and there are many situations, static correlation or interaction with other particles, where you have to consider that there are many particles. So the question of this research was the following: if you want to consider correlations in electronic structure theory, or in condensed matter, or in quantum chemistry, there is a very beautiful systematic way to go to this correlation regime. You know that write the wave function is in practice impossible, because you will need essentially an infinite Hilbert space or a lot of configuration that you cannot even storage in your computer. But you can do exponential ansatz. You can perform a rotation with an exponent. Exponential ansatz is something with the exponent that could be unitary or non-unitary in some cases, and you rotate that state, and then you eventually, with some techniques, you can reach a very good approximation for the real ground state, for instance. This is the spirit of coupled cluster, unitary coupled cluster theory, that's very popular in quantum chemistry. And actually people are starting to use in condensed matter, surprisingly. But whenever you want to put more than electrons, phonons or photons, now these ansatz look quite strange, and actually people don't know what to put in those ansatz. And let me go a little bit beyond. In the other extreme of the quantum many-body problem, you can also consider only bosonic systems, which are very interesting because you can have phenomena like Bose-Einstein condensation. But in this moment, people can realize in the lab bosonic mixtures, two different kinds of bosons. And then you have a beautiful physics, for instance, supersolids. Supersolid is a solid which is condensate at the same time, so breaking two symmetries. And then exponential ansatz, this kind of beautiful prescription that are in quantum chemistry, they are absent in those regimes, in those setups. So with these ideas, or trying to ask the following question, can you write efficient exponential ansatz for general quantum many-body physics? So I would like to provide a positive answer, and I will try to convince you that this is possible. So initially, one of the ideas behind this research is that in quantum simulation, you have several steps in the quantum simulation. You would like to simulate a system departing from some initial state that usually could be the ground state, evolving with some unitary. You have now the same state in the future, at the evolution, and then you can measure. Now this is the real system, and you would like to simulate it in a quantum simulator. Here there are several problems or several technical challenging questions, is the preparation, the evolution, and the measurement. If we talk about preparation, now the question is how you will prepare. This is why these exponential ansatz are so important now, because these unitaries can be in principle put in practice in a quantum simulator. Good, but as I told you, the problem is not only about electrons. There's also interaction with phonons in superconductivity. And now there is very popular field. Now it's a little bit old, but maybe only 10 years or maybe less, which is called polaritonic quantum chemistry. The idea of polaritonic quantum chemistry is that if you put a quantum chemical compound or something or some molecule in a cavity, then you can induce a change in the band structure or the excitation structure of the system, and then it's possible to develop quantum chemical reactions at the level of excitation levels. You are not restricted to work at the level of the ground state or dissociation at the level of ground state, but since you manipulate the structure of the excitation spectra, it is possible to do a quantum chemistry in some regimes that are in principle unknown in nature. And of course, open quantum systems, that actually all systems are open, but it is also interesting how to do it. Good. In the case of polaritons, so when you have these cavities, this amount of physics, this is a very rich physics. Essentially, this physics is determined by 3 parameters. The level of the electronic correlation, which is not surprising for quantum chemists, but also the interaction strength between the cavity and the electrons, and the photon number, so the quantity of the photons that can be in the cavity. And just to measure two things, excitation, polarons, cavity, photonics, Floquet band structure. The idea behind this is that somehow you will be possible to engineer new quantum many-body systems by manipulating these 3. Maybe you cannot manipulate too much electronic correlation, but you can manipulate the interaction strength with the cavity and the number of photons. Good. Now I would like to go directly to the result. In all these cases, the Hamiltonian can be written in this way, right? In principle, I am not putting any restriction. This could be Hermitian operators or not Hermitian operators. I just write those in some, let's say, Pauli words or something like this. For people working in quantum computing, in quantum information, this is a very natural way to write the Hamiltonian, because actually this is what we do. In other situations, let's say in the more non-quantum computing way of solving this problem, people usually write this Hamiltonian in 2 parts, the easy part and the difficult part. And the easy part is usually the non-interacting part of the Hamiltonian, the kinetic and the external potential, and then the other part that contains the difficult part, which is the correlations or the interaction between the particles. But let me write this in this abstract way for some people, or very trivial way in general. Now, if you want to ask several questions, for instance, in particular, what is the spectrum of this, or what is the eigenstate, the ground state or the ground state energy, you know that there are a lot of methods. This is just to put some of them, but these methods are not universal. So for instance, DFT is particularly well-suited theory for or weakly correlated electronic systems. And actually it's quite good, this theory at this level. The MRG or other kind of theories here or methods, they suffer in one way to the other if you want to promote it to other systems. In particular, if you want to do DFT for bosons or you want to do DFT for superconductors, then you have to develop a kind of new theory on top of this one. Quantum Monte Carlo, as you know, they suffer from the same problem in fermions, but they are very good for bosons. So in general, there is no numerical setup that you can apply agnostic of the system. The reason of these old methods is that they are based in the variational principle of quantum mechanics. So if you manage to find a small part of the Hilbert space where you think the ground state will be, and you manage to perform the minimization, eventually you will obtain a very good approximation for the ground state. Okay, and this is what I wanted to say you. So there are many ways to do it. This is just actually some modern ways to solve it. Now, since 10 years ago, it's very popular to try to do neural quantum states, so write neural networks for the states and optimize this in the way of machine learning. And this there is a renewed interest in what is called unitary coupled cluster because of the promise that you can implement it in a quantum computer. There is also the canonical transformations and some neural networks for open quantum systems. Now I want to bring your attention to these papers that for me are very inspiring papers. This is a paper from the group of Angel Rubio in Hamburg. This is a paper of Johannes Flick. And this is another paper from the group of Chan in Caltech. These papers have 3-4 years old, more or less. They're beautiful papers, highly technical papers. But the idea of these papers is to expand coupled cluster. And you can see from the title, coupled cluster theory for molecular polaritons, polaritonic unitary coupled cluster framework for electrons and phonons. So these papers extend coupled cluster to phonons with interaction with phonons, interaction of electrons. The interaction of phonons somehow is not very surprising and not very difficult because if you use perturbation theory, the Migdal theorem tells you that the phonons essentially with the first diagram can contain the whole interaction. So it's not very, so you can do perturbation theory. You're allowed to do perturbation theory, but with polaritons, you are not allowed perturbation theory because usually this regime is where the two parts of the Hamiltonian have equal weights from the electrons and from the interaction. But somehow, to me, it's a little bit surprising that you have to work too much or to write such a technical papers if you want to promote these theories to this interaction. What about you have electrons, phonons, another kind of boson and electrons? So you have all these kind of rich physics. Then you have to write maybe large and more technical papers if you want to promote it. Because coupled cluster theories are based in one beautiful property of electrons is that you have a separation by the Fermi level between occupied and occupied orbitals. But if you are in the set of bosons, you don't have this kind of limits because there is no Fermi level for bosons. And then you have to think in what could be a coupled cluster theory for bosons in these settings. Here also I put a paper that we did 2 years ago for the excitation spectra using a unitary coupled cluster. Well, but I think that could be a systematic way to do it. I think there could be a more systematic way. What I mean by systematic way is that you give me a Hamiltonian, and then I can give you such an ansatz. And this is because in practice, when I moved to Trento, they are very interested in interaction between bosons, which for many people maybe could be not so interesting, but I think could be a promise of simulation using bosons because this kind of new rich physics like supersolids. Okay, now I show you how this systematic way goes. So I would like to solve this equation, right? And here, let's say that I am interested in any eigenstate. Ground, the first excited state, the second excited state, and this is the equation I would like to solve. Now, there is something that is, to my surprise, for me was totally absent in my knowledge 2 years ago. I didn't know, I haven't heard about this word, or I have heard about this word, but I haven't read the papers. But it was very popular in I will say maybe a small community within quantum chemistry, which is called the contracted Schrödinger equation. The contracted Schrödinger equation is the following. If I take this equation here and I multiply by one of these operators here, and actually I have this freedom to do it. I can choose any way to write this. Even I can write h equal to h, and it also works. I will show you later. But I have this way of write the Hamiltonian. And then if I multiply here on the left, and I close this expression, of course, now I can say that Schrödinger equation implies this equation. Now, I will tell you 2 things about, or the most important realization of this equation. When you write in this way, you are not talking about anymore about wave functions. So your space is not anymore the Hilbert space, is the space of reduced density matrices. Why? Because this is an operator. In the case of electrons, it has at most two particle interaction. And this is H mu, which has at most two particle interaction. So this means that it has at most four particle interaction. And if you close this, you are talking about the four particle reduced density matrix of the electronic problem, which is related with, this is a constant here, with the two body reduced density matrix of the problem. And the people were trying to write, to use this to solve the problem at the level of the reduced density matrices. And you know that this is possible because the Hamiltonian only contains two body reduced density matrix. The functional is linear, so you will be able to solve it. Now you may ask why people are not using this direction, because of course it's not as simple that you go from something complicated, make a small transformation, and have something simple. The complication should be in another place. And it's because define the domain of two body reduced density matrix is a very difficult problem. But here you can see this situation clearly that you can write at this level. But the most surprising thing is that this implies the Schrödinger equation the other way around. I will prove it. So you take this equation, multiply by these weights of the Hamiltonian, and then perform the sum. And now you can see that F mu H mu is the Hamiltonian. So it's H squared. And F mu H mu is the Hamiltonian, but the sandwich with this guy is the energy. So it means that you have this equation. And you know that the solution of this equation, the states of this, the solution of this equation are exactly the solution of this equation. So therefore, this simple equation or equations, because now you have for H mu imply the Schrödinger equation. Now, what is surprising? Okay, you can find even older papers with this idea, but we put two of the most important papers, I will say, from David Mazziotti and Nakatsuji in Tokyo, where they 20 years ago were studying this approach. Now, and I should say, you can find this expression in all these papers of that year, but of those years, but the second equation, the equation after this, is immediately in the terms of electronic structure theory, because they are chemists and they were interested essentially in electronic structure theory. Now, there is a second step, is that you can decompose this in this way. This is an anticommutator of these two guys, and this is a commutator of these two guys. And finally, if you use this, you can find a way to produce a iterative way to produce a solution for these equations. This is the Ansatz. The Ansatz is iterative, so at the level n, you started with n minus 1, you have to multiply, or you can show that it do the job, you have this multiplication. The Ansatz is the sum of the terms in the Hamiltonian, H mu, with some numbers. I will talk about later about these numbers, and exactly here. This is a unitary, this should be unitary, this should be non-unitary. Why so? Because actually here you can interpret this equation as the gradient of a cost function which you don't know. So this result for me is quite surprising, because I have never seen, but maybe there are many situations, but I have never seen before a problem in which the first thing you recover is the gradient, not the cost function. In machine learning or in quantum computing, the first thing you put is the cost function. And of course, you later perform the gradient. But here you have a gradient. Actually, the way to solve it is the correct way will be to find this is equal to 0, but we don't know yet how to do it. So what we do is to put this equal to 0 and this equal to 0, the both equal to 0. If you do this, and you can recognize quickly the people working in quantum computing, this is the gradient, for instance, of the expectation of the energy with some operator in the unitary part. Now, for the same reason, you can see that it plays the job here for the anti-unitary part. And then with these two requirements, this will be a universal exact Ansatz for quantum many-body physics. And there are two important things. Here, the Ansatz has the same degrees of freedom of the original Hamiltonian, because you put exactly the same number m here. The only caveat here, or the crucial thing why this is still not easy solution, or you can see that still is we don't know exactly, we cannot say how many iterations, how many multiplications of these operators you have to do. But you see the level of complexity here at this level is exactly the same number of terms in the Hamiltonian. And now here I'm not talking about fermions or bosons, I'm talking about any general Hamiltonian. Now, it is surprising that some people eventually people forgot about these kind of things in quantum chemistry for the following reason. There are many situations in which only with one iteration, and you forget about this term, and only with this, you obtain very good results for the energy. And there are 3 papers in physical review letters in 2002, 2003, 2004, where they prove that only one term solved the many body problem. They prove. Of course, the proof is wrong because it will be impossible to rotate a trial wave function to the ground state with something that does not expand the entirely algebra of the rotation of the system. It's impossible. But there are proofs. And there are another proof that these proofs are incorrect, but they are published in physical review letter. This is historical. It's very interesting. And the debate took, I think, 5-6 years. Actually, Kutzelnich has another proof that this is incorrect. Yes.
Individual terms, the small h mu's, are they also permission?
Okay, so in general, you are the freedom to okay, maybe in this writing I am assuming this, but actually maybe this is actually a little bit okay, this writing is only if they are emission, of course, but this is it's much more, it's more flexible. You only put your h mu here, and then you have to guarantee that what you put above is emission, is anti-emission, and what you put here is emission. Yes, so this is only for this situation, but it's very general. So the only thing is h mu, but what is in the exponent should be anti-emission, and this should be emission. Yes. Okay, now an approximation is that you only take this part here, and then you take this purely unitary ansatz, iterative unitary ansatz. Good. If you take only the unitary ansatz, you can also work at the level of hexagonal states. There is a trick is to put weights here because a weight of zeros is 0. And then if you do this trick with some weights from maybe from 0 to 1, then you have this new gradient or this new, and then you can develop an algorithm. Actually, the algorithm is somehow intuitive here. To find these guys, you prepare your quantum state with these guys. Then you have the state prepared with these numbers that you find before. This is just a way to tell you that in this case the weighted energy is something like this. And then if you want to find the weights or the numbers of the next iteration, is actually the weighted sum of what we found using the contracted Schrödinger equation, which in this case is the expectation value of this commutator. But this is not surprisingly, this is actually something that you will find in a unitary coupled cluster exactly in that way. Exactly in that way, because you put some operators at the level of the exponent, and then you find that these are the gradients of that cost energy minimization.
Right, but A is a number, and if you put eta, which is undefined.
Exactly. Yes. Okay. Exactly. Now here there are two things, and actually here we are solving now the spectrum, not only the ground state. There are two things. The first thing is that this here, this equation here, is the equation exact for any eigenstates. I mean, for instance, it is valid if you have the ground, the fifth, and the seventh excited state. And if you only do the minimization here, you reach eigenstates, but you don't know which ones. This is the first thing. And the second is that what is going here is going down to the level of the minimization. So this, we put it in this paper, and this played a role because now in the let's say the most intuitive way, which is the unitary, actually now you are performing a normal minimization of the energy, and this can be seen like a learning rate. This is what we put, because you can manipulate how quick or how low or how slow you go to the minimum. What we did to solve the problem of reaching different eigenstates, to put some noise. And then,
but I guess my point is that the sum is a number, right? Because it's just the expectation values.
yes.
And also this is a number, and then eta is another free parameter.
It has another free parameter that actually.
In that sense, at A is not really defined.
A is not really defined exactly.
By this expression.
Exactly. So it's not uniquely defined because there are these A's, you know that they will converge, but you don't know neither how many, not neither how.
Okay, I see that essentially eta is the same for all A's.
Exactly, at this,
Okay.
yes, yes.
Okay, so
Yes.
in that sense, there is some minimum.
Exactly. And then, but somehow this only like moving around now the cost function that will come from the gradient, like the opposite. This is the results. This is maybe not surprising because now that you can solve this with many methods, essentially exact for linear H4, but you can find the details here. This is the entire eigenspectrum of the system given the minimal basis set that we use for H4. Good. Okay, but here.
So regarding H4, what's the relation between number of parameters that you have in your ansatz and like I guess the number in general of the all possible I guess generators in this I presume that you use relatively small basis set, right?
Yes, yes. Okay, it is very interesting the following. Here is electronic structure theory, so the Hamiltonian has a lot of structure. Okay, the first thing is the Hamiltonian has essentially the number of bases set to the 4 power. So this is the number of the parameters that we have in the ansatz. This is the first thing. The second is that this was done only with the unitary part, which also not surprising because actually I think you will obtain similar results, I think, with unitary coupled clusters, single doubles maybe. But here you have the exact, here no, you are not doing the differentiation between occupy and occupy orbitals. You are just putting what is in the Hamiltonian, maybe much more than the unitary coupled cluster. But the parameters at each step are exactly the same parameters that you have, or the same degree of freedom you have in the Hamiltonian.
But you have multiple layers.
You have multiple layers, yes.
So
by the number, yes. Yes. Actually, here maybe I don't remember exactly how many here, but could be something like 20 or 30, 20 or 30. There is we don't have any way to say if it is going to be, so, not even an estimate. Because for instance, in this case, in this particular case, because only we wanted just to run this for excited states, which was the first paper for excited states, it depends, of course, a lot of this learning rate. Parameters. In that case, I will say that it's not super surprising the result is because now we are in a very known territory where maybe coupled cluster single doubles gives you quite good results. And everything here is in that respect equal. The only thing is that the answer is a little bit different. But now what about if you have fermions and bosons, etc.? So this Hamiltonian here, B is bosonic. Okay, here I'm missing a hat. Here, this is the bosonic creation annihilation operator. It's a cavity. These are fermionic operators, plus, minus, up, down, say two levels. So, and there are now these numbers here that give you the strong weakly intermediate correlation regime. And this is all the interaction. Now, how do you construct your ansatz? Now what you have is the set of Schrodinger equations. And now I put it here. So, and now you can see, this is, okay, this is Hermitian, this is Hermitian, this is not Hermitian, this is not Hermitian. So they have these operators here, and you would like to solve these equations. Or you would like to find such eigenstates such that they satisfy this condition. Now, and now I'm going to your question again. Here, we'll have okay, say 1, 2, 3, multiplied by the number here was 3 sides. So 9, 10 parameters that we have in the ansatz. And the second thing, this Hamiltonian is much more simple in the sense that very few terms in comparison with electronic structure theory, because in electronic structure theory, you have really a lot. But here, let's say that's a very simple system. It's just a model Hamiltonian. Actually, could be a kind of joke for the experts in polaritonic stuff, because it's the most simple Hamiltonian. It's a kindergarten Hamiltonian for this kind of systems. But now you can see the crucial thing. The less number of parameters here, the less number of parameters you are going to have in your exponential ansatz. So it means somehow that the more complicated your Hamiltonian is, the more structure you have your Hamiltonian. And in those situations, usually with the unitary ansatz is enough. With the unitary part of the ansatz is enough. In this case, you are going to see something very interesting. Okay, first the numerical results. Here we compare the results of these ansatz with these methods. Okay, what is this jargon? QED, CCSD. QED, quantum electrodynamics, CC coupled cluster, S singles, D doubles. So quantum electrodynamics coupled cluster single doubles, which was developed in one of those papers that I showed at the very beginning. And 1, 2, 3. 1, 2, 3 is that since we are not used to work with bosons, what we do usually is to cut the maximum number of bosons allowed to occupy one bosonic mode. So if 1 is 1, 2, 2, 3, 3. So of course, the less you put here, the poorer it will be your ansatz, and so on. And you can see that, okay, this is what will be the Hartree-Fock theory of the problem. And you see that you are improving with the exact results, because here is you can find an exact result for the energy in this regime. Actually, this red line, which is QED CCSD3, actually has a very good energy in this regime. But the challenging regime of those systems is not the strong correlation regime or the weakly correlation regime. The challenging is the intermediate correlation regime. And you see that these methods fail here. Or these methods fail here at the level of approximation that they are using, which is single doubles. Now, this is maybe a crucial figure that answers several questions. Here is the convergence to the energy. So the main iteration is how many layers we have to put. This is the unitary ansatz, only the part of the unitary, and this is the entire ansatz. So you see that here you are converging eventually, but very, very, very small. So you have to really wait a lot. But if you put entire ansatz, actually in 3 steps, in 3 layers, you reach the ground state energy. What is the reason of this? The non-unitary part, as I told you, you can put H equal to H. So you put H equal to H, it will be like a stupid ansatz, or stupid way to write the Hamiltonian, but you can do it. Then the unitary ansatz, the non-unitary ansatz, will be equivalent to the imaginary time evolution, which actually always converge to the ground state as soon as the trial state has some projection with the ground state. But the convergence is guaranteed to the infinite time. Here is a little bit different because while the term contains exactly the terms of the Hamiltonian, the parameters are kind of variational. You can find this, you have the flexibility to manipulate these parameters. So you can think in the non-unitary term as a kind of dissipation. And actually in the last 2 years, or actually this year, I have seen several papers with the idea of using dissipative QE, putting some dissipative terms to go quickly to the ground state. And I think this is what we are seeing here. This was a kind of surprise result for this work. And this is another more because the energy at the end of the day is just an observable, but this is another observable, which is the occupation numbers of the fermionic sites. And again, you see that 1, 2 are pretty bad. Actually, they are continuous, where they have these steps here. QED CCS3 is really good here in this regime, but here in the middle, they fail completely to catch this physics, whereas the contracted algorithm really catch exactly what is going on in this system. Good, this is another result. This is now really, this is really for polaritonic, molecular polaritons. This is not in the paper. This is submitted, but not in the archive. I don't know why we didn't put it in the archive. So this is for H4 in a cavity, and this the energy. This is the comparison with the full CI, QED coupled cluster, and you see the behavior of the energy, and this is the occupation of the homolumu gap or the frontier orbitals in this molecular system. But the results are quite similar. This is like a baby example. This was run really in a quantum computer. This is H2 in a cavity. So we use actually only 4 qubits in the IBM computer, and this is QED Hartree-Fock here. We didn't compare with coupled cluster because we will be try to run this unitary coupled cluster polariton in the quantum computer, but we ran these ansatz here, and we obtained pretty good results for dissociation of H2 in the cavity. Well, this is essentially the idea of the ansatz. Actually, the result can be explained, I think, in these simple words. There are many ways, there are many technicalities, but actually you can write, given the Hamiltonian, you can write essentially any exponential ansatz independent of the kind of particles you are using. Again, you have the possibility of saying, I will take the unitary, I will take the non-unitary part. In that case, I will obtain something similar to unitary couple cluster. In the case of electrons, I will be obtain something similar to imaginary time evolution. But in any case, this is very flexible ansatz that you can use in many situations. But there is another idea behind this, is that the ansatz contains at each level of the iterations exactly the same degrees of freedom of the Hamiltonian, meaning that you have 4 numbers in your Hamiltonian, you have to find 4 numbers in your ansatz for many iterations that you don't know, of course, but for each iteration you know exactly the degrees of freedom. So we have been playing a lot in the last year also with a concept of operator learning. So now it's popular in physics to try to write neural wave functions, to write neural networks that contain the information of the wave function. But a wave function is a function for one system. You have your system, you have a wave function. Whereas, for instance, in the case of time evolution, you can say that for each Hamiltonian, you have a propagator. The propagator takes any initial state and gives you any final state. And this is what we are trying to do here. Is just the original paper. This is the original paper where they prove that as soon as they are a universal approximation theorem for functions, there is also one for operators or functionals. And the idea of this is that you, in the case of evolution, you enter with some initial state with some time t, and then it gives you, after you train, you can imagine that, of course, the training will be much more difficult than the wave function, but you can train these operators and you take out the state at another time. And we call it universal because you can enter with any initial state. And we wrote this paper. This paper was published 2-3 months ago for the case of open systems, a little bit still not very powerful because the Hamiltonians were time independent, but the system was open, and we managed to produce a neural propagator that resembles really the Runge-Kutta evolution. But I bring these ideas is because what we are thinking maybe is that it's possible to universal map Hamiltonians with a fixed set of operators, but different numbers in front of the operators, and map to the numbers in the exponent ansatz. This is not anti-commutator, this is sets. So there will be possible to do learning something like a kind of operator that learns from the Hamiltonian to the ansatz, and then you can go from these numbers to the next layer and this layer. And this is something we are now doing. Sorry. And the paper is not published, but something very interesting is that the error, maybe you have some error at the level of the parameters of the ansatz. Actually, the energy could be really, really good. So the error of the ansatz, maybe you have much more flexibility in the ansatz. You can produce very good energy results. And with this, I essentially conclude. So I have presented, I think, a universal methodology to write exact ansatz for quantum many-body physics. If it is efficient or how to implement it efficient, I think is a follow-up question that, of course, that will be very nice to think how to do it, which is based on the contract-Schrödinger equation that comes from the community of quantum chemistry and is agnostic of the constituents of the problem. What we are trying to do is this artificial intelligence-based Ruget model for the contracted eigensolver, and we would like to see if this can detect by manipulating or by learning how these parameters map from the Hamiltonian to the ansatz to learn about phase transitions, correlations, and maybe this could be also a good ansatz for the time evolution. And with this, I would like to thank my collaborators, particularly of the group of David Mazziotti in Chicago and the group of Li Pengchen in the Shenzhen lab. We were postdocs in the Max Planck in Dresden, and then he moved to China. And after 2-3 weeks in China, he now has a group of 70 people. So it's super crazy. I don't know, they are putting too much money. And the funding agencies, thanks to which I am here. So thank you very much for your attention.
floor is open for questions.
Yeah, thank you for your presentation. I remember in the slide you showed like you're only using like the unitary